Hi everyone, welcome back to Matthew Wister. Today we're going to be talking about alpha, beta, and gamma radiation in nuclear chemistry. So to start off, radiation is when an unstable atomic nucleus breaks down or decays to become more stable. So it's just when an unstable nucleus is producing a stable nucleus. Now there are three types of radiation. There's alpha radiation, beta radiation, and gamma radiation. So alpha radiation emits an alpha particle, also known as a helium nucleus. And you can see this in your reference table, in the table that says symbols used in nuclear chemistry. Right beside alpha, you can see that there are these two particles right here. Now an example here is we're going from Ra, which in this case would be our unstable nucleus, and it's producing Rn, our stable nucleus, plus the alpha particle. And we can see this again, there's this helium right here. Now alpha particles typically have a large mass and they have charge. They are low energy, meaning they have a low penetration and they can be stopped by paper, skin, or a thin layer of clothing. The second type of radiation is beta radiation or decay. This type of radiation releases a beta particle, also basically just an electron. And we can see this again in the same table where it's presented by an electron, or the symbol E. These types of particles have very little to no mass, they have a high kinetic energy, but they have a medium energy or penetration, and they can be stopped by aluminum. Type 3 is gamma radiation or rays. Now, this type of radiation is energy released from the nucleus, so it's electromagnetic waves. It has no mass or charge, and it has a high penetration, so it can be stopped by thick lead or dense materials, so it can pass through most materials. So, if you want to go from least to most penetration or energy, it would be from alpha, beta to gamma. Now, these three are essential for the basics of nuclear chemistry. They are the core of nuclear chemistry. And nuclear chemistry is just the study of how unstable nuclei form stable nuclei. So this contains components such as radioactivity, fission, and fusion. And scientists use isotope notation and nuclear equations to identify atoms and show what happens during radioactive decay. So what is an isotope in the first place? Well, an isotope, or radioactive isotopes, is an atom of the same element that has the same number of protons but a different number of neutrons. And these types of isotopes tend to have an unstable nucleus due to the uneven ratio of protons to neutrons. Now there are two types of notation for representing these types of particles or atoms. So there is AZX notation and there is hyphen notation. So in AZX notation, the letter A represents the mass number or the number of protons plus neutrons. The letter Z represents the number of protons, also known as the atomic number, and X is just a chemical symbol. Now, all this information you can find easily in the periodic table of elements. So for example, let's take carbon. C would be the chemical symbol because C is the chemical symbol for carbon. And then 12 is the average atomic mass, which you can find at the bottom of carbon. And 6 is the atomic number, which you can find above carbon. Now for hyphen notation, the only difference is that it doesn't include the number of protons or atomic number. It's simply the chemical symbol and the mass number. So here we can see C12. Now let's go more in depth about the specific particles that each of these radiation emits. So the alpha particle, which is represented by the letter A, or alpha, contains 2 protons and 2 neutrons. So its relative mass is going to be 4 because, again, in order to calculate the relative mass, you have to add the number of protons plus the neutrons. And the charge is plus 2. Whenever you're trying to solve nuclear equations or balance nuclear equations, you have to take the reactant side and reduce the relative mass by 4 and reduce the atomic number by 2. So here we have TH, also known as thorium, and according to the AZX notation, it has a mass number or relative mass of 230 and an atomic number of 90. So since we're reducing the relative mass by 4, we're going to be doing 230 minus 4. And since the atomic number is reducing by 2, we're going to do 90 minus 2. And so we're going to get 226 as our new relative mass and 88 as our new atomic number. And now all we have to do to find the chemical symbol is look at the reference table and see which element has an atomic number of 88. And that would be radium, also known as Ra. And if you want to check your work, you can just add 226 plus 4, and if it adds to 230, then you're right. If you add 88 plus 2, and it adds to 90, well, you're right. That's how you know it's balanced. Now let's talk about beta particles, or beta radiation. Now these particles have a relative mass that's effectively 0. Its relative charge is -1. But whenever we're doing the nuclear equations, we're going to keep the relative mass number the same, but the atomic number is going to increase by 1. So here again, we have our reactants. We have on our reactant side PO, or polonium, with a relative mass of 218 and an atomic number of 84. So in a beta particle, the relative mass is going to stay the same, so we're going to keep it as 218, but the atomic number is going to increase by 1, so we're going to add 1, and that's going to be 85. So then again, in the reference table, we're going to look for which element has an atomic number of 85, and that's going to be astatine, which is At. And again, we know that this is a beta radiation equation because in the product side, we see that a beta particle is being emitted. Now here we have a beta positron and gamma radiation. In a beta positron, the only difference is that it's the same thing as a beta particle, except it's an anti-electron. So in this case, the relative charge is +1 instead of -1. So a beta positron consists of an electron emitted when a proton in the nucleus turns into a neutron. So the mass is effectively 0 and the relative charge is +1. So the relative mass number stays the same, but the atomic number is going to decrease by 1. And lastly, we have gamma radiation, which is represented by the letter Y. So gamma radiation has no mass and no charge, so there are no changes in the mass or atomic number. Now here we have a nuclear equation, where in our reactant side, we have nitrogen, and on our product side, we see that a beta positron is being released. And the way I know that it's a beta positron is because here we have +1, which is the same thing as the beta positron. And you can also see this in your table of symbol used in nuclear chemistry in your reference table. Now, since we see that a beta positron is being released, we're going to have to keep the relative mass the same, but the atomic number is going to decrease by 1. So the mass is going to stay the same as 13, but the atomic number is going to decrease by 1, so that's going to be 6. Now, if we look at our table of elements, the element that has an atomic number of 6 is going to be carbon.